quick. Number 3, the graph looks something like this. It asked what root would it find, and it was kind of hard based on the graph. I mean, probably previous students had already drawn in there, in your book, probably. It said, what if you picked 0.95, which would be like right there? Well, that's really close to the peak, right, in the picture. So the idea was that then, of course, you want to check with Newton's method, does that equal 0? No. So what do? We ride that tangent line. And the idea was that I think that tangent line, it might not go quite that far that way, but it would go somewhere to the left of this peak, right? And so if it did go somewhere left of this peak, then the next one would come down this way, and eventually it would find this root right here, which is the negative 1.88 or whatever. Again, the key, when you get one with the, a polynomial that looks like this, tiny changes in your book, it talks about the butterfly effect. You've heard this. There's actually a movie, I think, of that. But the butterfly effect is small changes in an initial condition can have big changes. The idea is a butterfly flaps its wings in China, causes a hurricane on the other side of the world, because of, this tiny change, kind of like a small pebble in the pond, right? A little ripple, and then pretty soon it's a big, it can go. That's the idea. It's kind of one of the things behind chaos theory, okay? Tiny changes in initial conditions or initial sensitivity, right? Though there's a lot of different terms for it, okay? So that's the idea, because if I would just change this a little bit, that initial guess a little bit, so that tangent line would actually happen to fall on this side of that maximum, then all of a sudden my next guess would come back this way, and then again where it falls would depend, would it find this root, or if it was too close, so if this one came this way where it was too close to this max, then it might send it actually way over here and end up finding this root, right? So it totally depends on that initial condition. So that was kind of the idea on number 3. Okay, number 5, you were supposed to do your table. These are the numbers I came up with. You probably did not need to do this one. So you should have just had to go 3 rows, I think, didn't you? If you started with 0.5. Okay? If you started with something else, that's okay, but I think that was my suggestion. Steph. Okay, so if you start with 0.5, I got this. Now again, if you didn't hear me or you didn't think of or whatever, it said find the root between 0 and 1. So to me, 0.5, it makes sense. Okay, and there. So as soon as it said 3 decimal places. So as soon as you get agreement twice, in a row at the 3rd decimal place, you can stop. Okay, and then I did one more, and it actually then ended up that this one here actually ended up being correct all the way out to the 9. Okay, does that look familiar? Okay, all right. And then on 15, the idea was there were 3 roots for that one. The first one they had you try was 2, and didn't it alternate? Went 2, 5, 2, 5, 2, 5, right? So that was that cycling thing we talked about, where it was just kept taking you back and forth, so that didn't get a root. And then the other one was right near a max, I think, or a minimum. And it shot you clear out to thousands, 6,000, right? I don't remember what the number was, 6,000. So it sent you way, way out on the x-axis, but eventually it found its way back, right? Of course, the super-duper shortcut, you just did enter. Anybody count how many times it took? I didn't. How many? 9 times, which isn't bad, right? I mean, and so it comes back, and then pretty soon, it gets there pretty fast. So even though it seems like you're not making a lot of headway, that one we did was about as bad as any the other day. We had to go like 6 times, and it didn't send it that far away, but it was kind of bouncing around in there. Okay, so anyway, that's Newton's method. What are you going to need to remember about that? Matter of fact, this might, before you guys have to leave, this might not be a bad time talking about this, is, we've got this quiz next week on Wednesday. So the midterm's next Friday. We got the quiz. So we've only had one grade. We're going on our third week. We've had one grade. We're going to have a whole bunch here in a row. Okay, kind of a culmination of all this stuff we've been doing. We got a take-home thing that I'm going to give you today that's going to be due on Tuesday. All right, you can work together, organize a group of people to work together, a partner, whatever. You can do it by yourself if you want, but whatever. So that's going to be probably a 20 to 25 point grade, something like that, maybe even 30, like a quiz type grade. So that'll be due on Tuesday. On Wednesday, we're going to have this I call it the Chapter 4 No Calculator Quiz, okay? Let's talk about that just real quick. That's going to be on Wednesday, okay, of next week. Now, what's going to be on that? A lot of kind of short answer kind of questions. We have 3 theorems we're going to learn, and you're actually just going to memorize those and have to state them. So, for some of you, that you won't mind that at all. I mean, I just told you 3 of the questions that are going to be on the next quiz. State the extreme value theorem. State the mean value theorem. State the intermediate value theorem. Okay? I'm going to give them to you. You're going to write them down. You just memorize them. And those 3 questions are going to be on there guaranteed. Okay? So how about that? I just told you 3 of the questions. All right? Then there's going to be some other questions about the process of the things we have done in Chapter 4. Like optimization. Right? How do you find, now I don't want a list of the steps, I don't want that, but how do you find, where do you look maybe for a max or a min? You know, where the derivative is 0, where the derivative is undefined, where at endpoints, you know, that kind of stuff. So those kind of questions, not calculating things, right? That's why it's a no calculator quiz, right? I'm not going to ask you to find max and min or that kind of thing, but it'll be more about the process of what's happening. And so when it comes to Newton's method, right, describe the process of Newton's method. You know, the idea like we were just talking about, that we're looking for a root, we're going to start with an initial guess, plug it into the function to see if we get a 0. If not, we will ride the tangent line to the x-axis and then check and see if that is the root or gives a 0. And if not, we repeat that process until it eventually zeroes in on the root. Or I might ask you, what could be some problems of Newton's method? Well, we just did 2 of them, right? It cycled around. Or if you pick a guess that's close to a maximum, it may take you a long ways away. That kind of stuff. Those kind of questions. Okay, and we'll talk more about it as we get closer. But just to give you kind of a heads up as to what that is about. Okay? All right, so we'll be doing some homework on these. And then there could be some questions kind of like about the theorems, which we will be doing over the next several days. Today's homework, Monday's homework, right? So there'll be those kind of questions as well. So you'll see as we do. Okay? All right, I know in the other class there's a couple people said they were going to be gone tomorrow and Monday, so I want to talk about if anybody's in that situation. I wanted you to know about that. Okay? And then, of course, we're going to be working in the packets, and that's the midterms that are then on Friday and Monday. So those are both, the 2 midterms are both 30-point grades. This quiz is probably somewhere in that neighborhood. The take-home is somewhere in that neighborhood. And then the 4 packet grades, right? We talked about the 7 points per packet, like 28-point grade, right? So that's like 5 grades, 5 kind of quiz-type grades right there in a row. Okay? All right. So let's go to sample 2. Oh, I don't have sample 2 of it. Maybe it would be worth quickly going through the answers. Now, if you don't want to write the answers next to the problem because you haven't done them all yet and you'd rather just write them on the back of the packet or something, that's up to you. You could do that if you want. Otherwise, I thought I'd go through the multiple choice answers at this point. You hopefully had a chance to try a lot of them. And so you can double check here to see what you've got questions on. So here's what I've got. Or you guys tell me. Number 2. E. Number 3. B. Now that actually is one of our theorems for today. So I'm going to talk about that one, but it's pretty much common sense. So I think you could have gotten that one. But anyway, that one's B. But let me just read it a little faster. 4 is C. Of course, if you can't flip fast enough, it's going to slow me down. Number 5, I got D. Seven is C. 8 is A. 9 is E. 10 is B. I think we did that one, didn't we? 11 is B. That was one that we're going to learn with our theorems here Monday, actually. That one. 13 is C. 15 is A. 17 is D. 20 is B. 21 is C. 22 is C. 23 is D. 25 is B. 26 is D. What's a normal line? Related to a tangent line. What do you suppose? What would be the options? Does it say? Oh, there you go. Oh, it's it. That's why you're like, yeah, I didn't know. You probably saw the word normal and said, I give up. Yeah, it's perpendicular to the tangent line. Okay, there you go. I didn't know it's it. It's perpendicular to the tangent line. So that just means you would do the derivative to get the slope, which would be the tangent line slope. And then what's perpendicular slope? Opposite reciprocal, right? So if you do the derivative and you find the slope is 2, then the normal line would have the slope -1/2. And then you just do your equation every time. Just do your point slope. Take that slope, take the point. Same point, right? It goes to that same point. So, okay, so that's 20. What was that? 26? 27 was B. 29. 29 is actually the definition of the derivative. It's the weird form of the definition of the derivative that we didn't do very often. That's what that one is. And that's what, so it's kind of like that one we talked about yesterday. That's supposed to be C. Okay? But because that limit is not really a limit, it's a definition of derivative. 30 is A. 31 is also A. Did we really do a whole bunch in a row here? I got a circle of Calvin's sake. That's a fun. Okay, 31 is A. 32 is B. 33 is D. 34 is B. We didn't? Okay, why did I circle? I was going to say, I got so many circles. 35 we do?
What did you say 33?
33 was D. 32 is B. So 34 we didn't do. 35, C. 36, E. 37, D. 38, B. 40 is C. And 45 is C. All right. So, spend a little time talking about those. Where do you want to start? We can do a couple for sure. 11. Oh yeah, I tell you, yeah, 11 was one we said, yeah, we're going to learn about. Actually, we're going to learn about that one on Monday, so let's skip 11. I want to comment on 3. This is a theorem we're going to learn today. Suppose that f is continuous defined for all real numbers. That's going to be a big deal for us. We're continuous. Continuous, of course, means there's no breaks or no gaps or nothing like that. F of -5 is 3, and f of -1 is -2. Now, what have I told you in the past? If you're given information like this, what does that mean? What did they just give you there? Couple of points. What would be a good idea? Plot it. Yeah, I would definitely say plot it. So here's the f graph. So that means at -5, you get a value of 3, and at -1, you get a value of -2. Now it said if f is equal to 0. Now what's that mean, f equal to 0? That's where it crosses the x-axis. That means the y value. So if the y value is 0 for only one value of x, in other words, if it crosses the x-axis only one time, where's it got to be? It's got to be between there, right? The only way it can get from here down to here, unless it jumps, is to cross the x-axis. And it's not going to jump because it's continuous. So it's got to cross somewhere between -5 and -1, and this is the only one where that is true. Okay? That is a consequence of something known as the intermediate value theorem, which we're going to learn today. Okay? All right, but again, I don't think you need to know that, right? I think common sense, if you plotted those points, just common sense would have told you that. Okay? All right. Anyway. Keep going.
13.
What else? 13. Here you guys go again. When I say next, you really mean next, don't you? All right. We're supposed to find y prime. Right? This is just a straight out implicit differentiation problem. So derivative of x is 1. What's the derivative of y? Y prime. Not y prime, just y, right? The y prime. The derivative of y is 1. Tack on a y prime. Equals, what do you got to do here? Product rule. Derivative of x is 1. Leave the y alone. Plus x left alone. Derivative of y? Y prime. Now what's the next step in implicit? Get the y primes on one side. So let's move them to the left. Y prime minus xy prime equals, and then let's move that 1 over there, y minus 1. Take out a y prime. You got 1 minus x equals y minus 1. Divide by 1 minus x. You get y prime equals y minus 1 over 1 minus x. Now you run into the issue that I have when I'm grading the gateway test and I'm grading your implicit differentiation problems, because is that up there anywhere? That is not up there anywhere. Well, what if we'd have got the y primes on this side?
Then y prime would be negative.
Well, everything would have been opposite, right? But it's the same answer, because what you can do is take out a -1 on top, and this becomes negative y plus 1, which of course is just 1 minus y. And then take out a negative on the bottom, and that becomes -1 plus x, which of course is just x minus 1. So you take a negative out of the top and the bottom, the two negatives cancel. It's kind of like having -3 over -2. That's the same as +3 over +2, right? Well, that's what's going on here. So y minus 1 over 1 minus x is the same as 1 minus y over x minus 1, which is c. So you just had to take a negative. If you did it that way, just take a negative out of each. So when you guys would do your gateway test, some of you would get the y primes on this side, some of you would get the y primes on this side, and then I just had to know that, okay, both of those answers are okay. Okay? Just depending how you did it. All right. I am not going to do number 15. Okay. Yes.
22.
All right. 15. Maybe sometime I can do it. 22. What are all the values of x for which this graph is concave down? Really good problem. This, again, to me, is one of those that should be this kind of, I hate to use the word easy, but it's you know, what makes the AP test hard and the packets hard, especially initially, is we're seeing a lot of problems that are just different than we've done. They're just worded differently. You've got to really understand the concepts. You've got to put things you know together in different ways than you've done before. But there are some questions that are just like ones we've done on our quiz, stuff like that. And this would be one of them. See, so when I say easy, what I really mean is, hey, here's one that isn't weird. This is one that's just like ones we've done. How do you tell when a graph's concave down?
Y double prime is negative.
Second derivative is negative. How do you tell when second derivative is negative? Do a number line, which means find when the second derivative is 0, right? So this is just like a local max problem, just a basic chart problem is what this is. So this is 3x squared minus 12x. Now we have done a lot of these for a while, so it takes a little getting used to in the practice, but you know when it comes to the actual test, we would want to be able to do well on this. So 6x equals 12, x equals 2. It's our only possibility. We put that on a y double prime number line. Pick a number here, pick a number here. Here's our second derivative. We plug it in, put a 1 in here. 6 minus 12 is negative. Put in a 3. 18 minus 12 is positive. So this graph is concave down to the left of 2. Right? So that's what I mean by, you know, compared to that instantaneous rate of change versus average rate of change problem. And it had A's in it. You know, those are tricky. Okay? This would be one we would want to have by next week. We'd want to feel pretty comfortable. That's why we do 4 packets. So we see it a couple of times for sure before then. Okay, what else? Get into the calculator section. Maybe not many of you got that far, but if you did, let's start. Let's talk about 29 in just a minute. This is the one. This is an alternate version of the definition of the derivative. Now again, here's why you should think of it that way. Because doesn't it look like slope? Right? Doesn't that look like slope? It looks like slope. It's subtracting y, subtracting x's. The reason it's derivative is it's saying, okay, we got 2 points, and so the y value of this point would be f of x, the y value of this point would be f of a, so the slope would be f of x minus f of a, that'd be the y's, and then x minus a, and then we're doing the limit as x approaches a. So as x gets closer and closer to a. Well, that's what you have. You have the 2 points becoming 1. That's why it's a definition of the derivative. Okay? So so what they're saying, if this equals 0, what they're really saying is if f prime equals 0, which of the following must be true? Right? So that's what you had to do to get this one. You had to recognize that this is f prime. Oh, if f prime equals 0, the limit does not exist? That's not true. F of a does not exist? That's not true. Oh, there it is right there. F prime of a is equal to 0. In other words, you're saying, oh, that thing is equal to f of a, or f prime of a. So that's why that one is C. Okay, just recognizing that that is the derivative. Usually the one we see is the a plus h one. That definition, that's the one that's used more often. But this one is too. But you should recognize it just because of slope. All right. What else? $31, $32, $35. Okay, let's. I don't think these will take too long. Let's do a couple of those, and then I'll just give you some more. You got some more time to work here today on it. But you're going to have some book homework, and then there's the take-home test. You know, again, I want you to work more on that outside of class. Quite honestly, we should take care of the homework here first. Okay. Today I'm actually not going to give that to you until at the end, or when you guys. I know some of you have to leave. But, so let f be a function that is everywhere differentiable. Okay, everywhere differentiable. Now, that term is going to be more important over the next couple of days. We've talked about the derivative exists everywhere. Derivative exists everywhere, so there's no sharp points, no gaps, no jumps, no break, nothing weird at all. Differentiable means smooth, basically, nice and smooth. Okay, so that means the derivative exists everywhere, including in between these places. That's what that means. So if f prime is always increasing, well, this is just a basic chart question, really, isn't it? If f prime is increasing, think back to the chart. What happened when f prime was increasing? What does that mean about f? concave up. Is that down here anywhere? No. This is always increasing.
I did like a
So,
slope field.
so there's something. Oh, you plotted some points, kind of just to look at it, plotted the slopes, because that's what these are, the slopes. So you did it kind of an F graph. Okay. Well, what else? Look at this. What else stands out about this F prime row? I mean, you could plot that. I don't think you'd have to. Wouldn't this be a pretty interesting piece of information, right? When does F prime equal 0, right? So we're right. I mean, F is concave up, okay, the whole time, all right? But if F prime is 0, we also know that's a stationary point, like a local max or min. So this is almost like a number line, isn't it? This is basically saying that on the left, F prime is negative. On the right, F prime is positive. So what's that tell you? A local minimum, right? If F prime is negative on this side and positive on this side, that means F is decreasing then increasing. So since it's concave up the whole time and you get that, then isn't it A? Right? And that, I'm sure that's kind of what a little graph or slope field would show you too. Okay? So it ends up being that. Okay? Good. Then 32. 32 is a little bit interesting. I think the hardest part of this is just the wording. Certain species of fish will grow from X to this each year. In order to sustain a steady catch, a limit of this, which is just those subtracted, are to be caught, leaving X to reproduce each year. In other words, it's going to grow from this amount to this amount. So that's how many they want to let them catch, right? However many new fish, they're going to let them catch that many, so that way there's always the same amount of fish at the end of the year, right? That's the idea, okay? What is the number of fish that should be left to reproduce each year? In other words, X. How much should be left, which is what they're saying X is, so that the maximum catch may be sustained from year to year, okay? Well, how would you represent the catch? Well, it says it right here. The catch is this amount right here. How many are there at the end minus how many were there at the beginning? That's the catch. That's what we want to allow to be caught. So I'm going to call that function C for catch. And that is X times 15 minus X minus X. I mean, you know what I mean? This is an optimization problem. We want to maximize the catch. So the first step is always identify it and write an equation for it. So they actually gave you the equation for it. It's just it kind of gets lost in all those words, I think, is probably the problem. So actually, this is a pretty simple one, even though you can use your calculators. 15x minus x squared minus x, which would be what? 14x minus x squared? That's actually what we're talking about, maximize. Well, that's just a simple upside down parabola, right? So C prime would equal 14 minus 2x. Set that equal to 0. X would equal 7. And since that's our only candidate, I don't really need to justify it or anything because it's a multiple choice problem. I don't really care about that. But also I could say, hey, this is just a simple upside down parabola. The max is going to be where the derivative is 0, which is at 7 million. So they should have 7 million fish in there to maximize how many would be caught. Okay? All right. And then 35, you said? The graph above shows the distance from a reference point of a particle moving on a number line as a function of time. So moving back and forth like on the x-axis. Which of the points marked is closest to the point where the acceleration first becomes negative? Okay, so this is position. Now remember, we got position. Here's the key to this, I think, is thinking that this is position, velocity, acceleration. This is the position graph. So when they say the acceleration first becomes negative, think of the number line. Think of the chart. The acceleration is like the second derivative, right? So when the acceleration is negative, what's that tell you about position? Concave down. So this question is really saying, where does this graph first become concave down? Which is where? Point C. So it's concave up. So this whole time the acceleration's positive. Now again, that's that thing about acceleration. What's happening is you're slowing down. If this is position, this is like coming back towards Bismarck, right? You're away, you're in the positive, you're east of Bismarck. You're coming back towards Bismarck, slowing down, now moving away from Bismarck. Well, your acceleration's always positive then, right? Because what's happening? The slopes are what? Decreasing? No. Increasing. They're negative and getting less negative, and then they're positive and getting more positive. So this whole time your slopes are increasing, which of course we know means its derivative, the second derivative, is positive. First becomes negative when it switches to concave down. Okay? So anyway. All right, let's move along here because I want to leave you some work time, and I know some of you have to leave. What time? 10 after? Yeah. Okay. All right, so let's get your notes out here, and we're going to talk about two theorems. And I'm not really in favor necessarily of memorization and the theory part. I mean, the theory part's okay, but it's not something we emphasize. But there are a couple here that I think are important enough to maybe memorize. Okay, and what is the extreme value theorem? Now, extremes, of course, mean mins and max. We've been doing a lot of work with that, right? Our last quiz was a big part of that was finding mins and maxes. So the extreme value theorem says, let f be continuous on the closed interval AB. Now, while you're writing that, I'll just mention the title of this section. This is 4.8. The title of this section is Why Continuity Matters. So you'll notice on the two theorems today, they're about continuous functions. So continuous functions, remember, are smooth, excuse me, not smooth, but they connect. Continuous functions are connected. There's no breaks, there's no holes, okay? There's no jumps, no vertical asymptotes, that kind of stuff. So the idea here is, if we know a function's continuous, what good information does that tell us? Well, this theorem is one of the things it tells us. It tells us, okay, if you've got a continuous function like a polynomial, sine, something that you know doesn't have any of that stuff, and you're talking about a closed interval, then the function has to have both a max and a min value somewhere in that interval. This is called an existence theorem because it guarantees the existence of a max and min. It doesn't tell us where to look. That's what we did in our optimization problems. We said you look at the endpoints, you look at where the derivative is 0, and you look at where the derivative is undefined. Now, we had some problems where there was no max. Think of an upside or a minimum. Think of the upside down parabola. Is there a minimum on an upside down parabola? Well, at the endpoints, right? But what's the only time we'd have a problem where we'd say there is no minimum? Like if you had an upside down parabola. If there aren't any endpoints, right? Didn't we talk about a situation where there were no endpoints? Now, one of the things that's going to happen in your homework questions is it's going to give you an example of what I just gave you, and it's going to say, why doesn't this violate this theorem? Because if it's a theorem, it's got to be true, right? It's been proven. So when you have a theorem, you have the hypothesis and the conclusion, if then, right? Those of you that were in computer programming, we talked about if-then statements. We talked about that kind of a thing. If the function's continuous on a closed interval, then f has to have both a max and a min. Well, I just talked about an upside down parabola. It doesn't have a min, it just has a max. Well, there's no closed interval. This only promises that there's going to be a max and a min if the function's continuous and you have endpoints, right? So that's where the min could be. So it doesn't violate the theorem if it doesn't contain the hypothesis part, the if part. If your parents say to you, if you get an A in calculus, then I'll buy you a car. That'd be great. I'd really feel a lot of pressure. If you came to me and said, hey, I get a car. But if they said that to you, and this is the one we talked a lot about in programs, if you get an A, what has to happen? They have to buy you a car, right? Unless they lie, right? Well, this is not a lie. The extreme value theorem is not a lie, okay? So if they keep their promise, if you get an A, then you get a car. What happens if you don't get an A? Joe, what happens if you don't get an A?
You don't get the car or make it.
Listen to the promise again. If you get an A in calculus, then I will buy you a car. What happens if you don't get an A? They didn't say. Now, if your parents are like my parents, what they really meant was, if you get an A in calculus, I'll buy you a car, and if you don't get an A, you ain't getting no car. Right? I mean, that's what they meant. That's what you probably inferred, but that's not what they said. They said, if you get an A in calculus, then I'll buy you a car. If you don't get an A, they might say, what the heck, I'll get you a car. Probably not, but would that violate their promise? If you didn't get the A, and they bought you the car anyway, would that violate their promise? That wouldn't violate their promise. Their promise was, if you get an A, then I'll buy you a car. So if you don't get the A, then the promise doesn't exist, right? It doesn't say anything. You maybe get the car, maybe you don't. Okay, well that's the same thing's true here. If the function's continuous on a closed interval, then there has to be a max and a min. Okay, let me show you an example of a situation then where the hypothesis is not true, and you don't have to write this down, but here would be a function there's a hole right there. Okay? Now, is this function continuous? No. But is there both a max and a min?
Yes.
Yeah. There's a high point at the right edge, the right endpoint, and there's a low point. But it wouldn't have had to be continuous, right? It just happened to be. The theorem didn't say anything about that graph. The theorem does not promise that there will be a max and a min because it doesn't meet the standard of the if part, right? Because what could have happened is there could have been a hole right here. Now, is there a minimum in that one? Is there a lowest point? No. Let's say that's right there at 1. This graph goes 1.01, 1.001, 1.0001. You can get as closer and closer and closer to 1, but there is no minimum value. No matter how close you get to 1, you can get a little closer, right? There's no minimum in that graph. But this doesn't promise that there will be one because it doesn't meet the standard of the hypothesis that it's continuous, right? Okay, so you're going to have some questions like that, right? All right, and then, of course, this doesn't say anything about where to find them, but we know derivative is 0, derivative's undefined, and endpoints, that's where we look. Yes?
So if you had a horizontal line, would your max and min be the same value?
Good question. What about the sine function? It's not quite the same as yours, and I'll get to yours in a minute. But if you had the sine, I've said this before, if you had the sine function and you only went from 0 to, say, 6 pi, what's the maximum? 1. Now, it happens a couple of times, right? But the max is 1. What's the minimum? -1. So if you had a horizontal line at 2, right, that's continuous. And let's say you only went from here to here, so it would have a closed interval, so it would meet the standard. So it has to have both a max and a min. What's the biggest value on that line? 2. Is there any values bigger? No, so it's the biggest. What's the littlest? 2. Are there any littler? No, so 2 is the littlest. So the answer to the question is yes. 2 would be both the max and the min, right? So that wouldn't violate this either, right? It doesn't say they have to be different. All right, so that's that theorem. So one of the questions on the quiz next Wednesday will be, state the extreme value theorem. Now, if you're off a word or two, this is a pretty easy one actually. The next one's a little harder to memorize maybe. you better have that the function's continuous and it's a closed interval. Now, if you say something that doesn't make any sense, that'll be bad. Like I've had people say, let f be on a continuous closed interval. Well, that's saying that the interval's continuous, not the function, right? I mean, so the words matter, right? The function's continuous on a closed interval, okay? So you do have to be a little careful there. All right, here's the next one. Intermediate value theorem. I'm noticing that I did not write in a straight line or on a horizontal line. Of course, you guys are probably used to that. I probably never do. I think that's being left-handed. The intermediate value theorem. Now, when you hear intermediate, think in between, right? Extreme value makes you think max and min. Intermediate makes you think in between. Between values. Let f be continuous on the closed interval a, b. Notice the same thing. But we have another if part to this. And let k be any number between f of a and f of b. Now, I think your book, they use y instead of k, I think. But now, couple important things on this. What's f of a and f of b in this scenario? The y values where? At the endpoints, right? A and b, we're on a closed interval, so a and b are the endpoints. F of a and f of b are the y values at the endpoints. So k is some y value between the endpoints, right? That's what that means. K is any number in between the endpoints. And then it's y values, okay? All right. Then so that's where kind of the between comes from. So if you have this, if you have a continuous function, you got a closed interval, and k is any value in between the endpoints, then there has to be some c between a and b. Now remember, a and b are x values. They're your endpoints on the x-axis, right? So there has to be some x value in between, we'll call it c, that where the y value at that point, f of c, is equal to k. Now, again, it doesn't make a lot of sense. So if you want to translate that a little bit, now I think when you write this on the quiz, you ought to write it this way. You might be able to get credit if you translate it into a little more ordinary language, but you got to be careful because that's a little tougher to do. But it basically says this. F will hit all y values, and again, this would not be worth full credit on the quiz if you wrote this blue thing. Okay, this is just to let you understand what's going on. This is the last part I'm talking about, the then part, the conclusion. It basically says that f will hit all y values between f of a and f of b. Okay? So I usually talk about this one like if I was going to drive from here to Grand Island on Highway 30. If I was going to leave Kearney at Cabela's and go to Grand Island on Highway 30. At some point in time, I would have to be in Gibbon, right? I would have to be in Shelton. I would have to be in Wood River. I would have to hit all points on Highway 30 in between there, right? What's the only way I could not? Well, if I didn't go on Highway 30, or if I went on Highway 30, but I beamed myself at some point. Like when I got to Gibbon, right, I transported myself straight to Shelton. Then I could, but then what would that? It would be continuous, right? There'd be this gap, this jump, right? So so again, this is saying that if you know a function's continuous, so you see how this is like number 3? We had that point over here, and we had that point down here, and we knew it had to cross the x-axis somewhere. That's where this is used a lot of times in finding roots, right? We did it with Newton's method. If you get a y value that's positive and then you get a y value that's negative, the intermediate value theorem says if that function's continuous, you have to hit all the y values in between them, right, at some point. That's what that's saying. You'll hit all the y values between f of a and f of b. Now, what you got to be careful of is, let me give you this example here. So let's say I got this and this. This is 6. This is 5. This is 3. And this down here is 1. What does the intermediate value theorem say in this problem? That the function will hit all the y values between what two numbers? 5 and 3. 5 and 3. Not the maxes and the mins, right? This says between the endpoints. I start at 5 and I end at 3 means I had to hit all of the points in between 5 and 3. Now, did I go the other way a little bit? It'd be kind of like I go from here to Grand Island. I start in Kearney. I'm going to take Highway 30 the whole way. I start in Kearney. I end in Grand Island. That means I had to hit every point between Kearney and Grand Island. Now, could I went to Elm Creek, turned around, and come back and went to Central City, and then come back and stopped at Grand Island, right? Could have, but that's irrelevant. Right? I didn't have to hit those points, but if I started in Kearney and I ended in Grand Island, I've got to hit all the points in between there, but I might have hit some extras, and that's what this does. Started at 5, ended at 3. I hit some extra points up there at 6 and down at 1, but I had to hit all the points between 5 and 3 at some point. Okay? So the key is you understand f of a and f of b are between the endpoints. The endpoints are what matters, not the max and the min. All right. So, last thing then. I was telling you a minute ago how sometimes you get a function that doesn't meet the requirements. But it still could. The question to be, does the conclusion still hold? So here's a function. Is it continuous? This function? It's not continuous. So does this promise have to be kept? No. Right? The promise doesn't have to be kept. But could it be kept? It could be, but it doesn't have to be. And so is this one kept? Does this function hit all the y values between 5 and 3? It does. So the promise was kept. The conclusion was held. But it wouldn't have had to be because the function is not continuous. Now, if I put the whole here, now is the conclusion kept? Does this function hit all the y values between 5 and 3? No. But it's not a lie because it doesn't have to. It only has to if the functions are continuous. Okay? So that's the kind of questions you're going to be asked about this kind of situation. All right, so I'm going to let you get to work here. In your assignment sheet, there's 4.8. 4.8 are the problems to do. Okay? 4.8 and continue with sample 2. Right? Would be my suggestion. 4.8 homework on the sheet. That's number 1 priority. Sample 2 would be good to be getting some more of that. Now tomorrow you're going to have work time. So you're going to have to, you're going to have to kind of think long term here between now and next Wednesday. Right? About planning your time. And I'm sorry, I know there's at least one person who's talked to me about some other activities, trips they have to take, whatever, which is tough. But so you got to plan your time. So you got some packet work you need to continually get at. The take-home thing. So have some time, a couple days where you can spend a little bit of time working on those or getting together with people. It's not a horrible amount of time for any of these things, but it is probably a little more than we've spent some days. What's that? Did I record? I did.